Good morning, advanced placement physics students. I am away at an Energy Academy field trip, so I am here in spirit. Okay, well, maybe not spirit, but I'm here on that little data key that's recording this video. And here's what's coming up. Believe it or not, the last assignment we did was the last assignment of Unit 5. So what I would like you to do today is the following. I'm going to have the substitute teacher hand out the Unit 5 take-home test. Okay, and here it is, right here. So if you're watching this on video, I think you can freeze frame this, or and use it. It'll also be online eventually. I'm having trouble getting stuff online right now, so you're going to have to be patient. So this is the Chapter 10-11 Unit 5 take-home test. And you can work on that today. Then we're going to set up the Unit 6, Chapter 13-15 calendar, which we're going to do here in just a minute. I'll set up your assignment list and calendar for Unit 6, and then I'm going to lecture on Assignment 1. I'd like you to read the book, read 13.1 and 2, and then do the example problem, and then these 4 problems. And once I'm done with this, you can have problemathon, and what should you do in that problemathon time? Well, work on Unit 5 assignments, work on the Unit 5 take-home test, and work on Assignment 1 for Unit 6. Hey, when I get back on Thursday, please remind me to show you the conservation of angular momentum demonstrations that we didn't have time to get to on Monday, because I really want to show those to you, and they're worth having fun with. So anyway, let's get started. Here is your calendar for Unit 6. And so if the substitute teacher could right now just press the enter button on the document camera, that will pause the video long enough for you, for the students to copy down the calendar. This will take us all the way to the end of the semester. Today is December 4th, Tuesday, and then here's Thursday, and then next week, Monday, Tuesday, and Thursday. Thursday will be the Unit 5 exam. So get the take-home test done and get the Unit 5 notebook done by this day here, because the take-home test and the notebook and the exam will all be on this day for Unit 5. Unit 6 will continue, and I will probably give you the Unit 6 exam on this day right here. That gives us one makeup day, and this is the end of this first semester. So somewhere in here will probably be the Unit 6 stuff we'll be due. This is the week before winter break, and it's kind of weird. I think that Monday is going to be a Friday schedule, so we'll have 2, 4, 6, and then Tuesday and Thursday will be odd period blocks. That's because Friday is a furlough day, Friday before winter break starts, so that's good news, I guess. So it's an extra day off for all of us. Okay, so go ahead and pause this now so that everyone can copy it down. Okay, go. All right. So let's let me do the lecture on Assignment 1, and so if you're not done with assignments 1, 2, 3, 4, 5, and 6 from hey, make room in your calendar, in your notebook and all that. You know what to do. Okay, so let's get going here. We're going to be talking about this. Newton's law of gravity. By the way, chapter 13 is my favorite chapter because we're going to get into astrophysics and we're going to learn about the radius for of black holes and all that kind of stuff. So it's pretty cool. It's very cool stuff. Now, Newton, while he was figuring out all his laws of motion, also had a lot of curiosity about gravity. Specifically, why does the moon stay in its orbit? Or what, maybe not why, but why doesn't the moon come crashing down to the Earth the same way that an apple falls from an apple tree? And so this got him thinking about force at a distance, and he tried many different ideas before arriving at a solution that correctly predicted how planets and moons move in circles around each other, and it just worked very well. And so we're going to talk about that theory. Now, here's the bottom line of the theory. I mean, this is the real essential aspect of Newton's law of gravity. Suppose you have one massive object. It could be planet Earth, for example. And out here is another massive object, perhaps the moon. Those are the two objects that Newton was really into. Okay, now, according to Newton's third law, third law, if these objects apply forces to each other, they have to apply equal and opposite forces. So, and what he supposed was this: these objects apply forces to each other. The Earth applies a force to the moon towards the Earth. The moon applies a force to the Earth towards the moon. And these forces, according to Newton's third law, have to be the same in magnitude but opposite in direction. I should make this a little longer, I think. Okay, so now a brilliant question is, why do these objects apply forces to each other? And Newton famously said, "I feign no hypothesis," which is a fancy way of saying, I have no idea. Don't ask. Okay? Or at least, that's not my problem. I have no idea why gravity works. I just know that it does. I mean, people said, how can you have force or action at a distance? How can the Earth apply a force to the moon when they're not even touching each other? Well, Newton had no idea. Why? He just said, hey, let's just suppose that it does, and let's figure out how to describe these forces of gravity. This is the force of the moon on the Earth, and it's equal, but in the opposite direction of the force of the Earth on the moon. Okay? And together we just call that the force of gravity. So, what is this force of gravity? What does it depend on? How do we describe it? And Newton very successfully did that. He said, let's do this. Let's say that the mass matters. So we'll call this object 1 and 2 instead of Earth and Moon. It doesn't really matter. And it says, hey, the mass of object 1 matters. If I make object 1 twice as massive, guess what? I get twice as much force of gravity, force of attraction between the two objects. And same goes with the other object. If the force of gravity is directly proportional to the masses. Makes sense. And it also depends on how far apart these objects are. And we're going to call that R. R is the distance between the center of object 1 and the center of object 2. Now, One would think, and one would be correct, that as you make these objects farther and farther apart, that the force of gravity would get weaker. And that's exactly what happens. It's inversely proportional to r. But wait, it's not just inversely proportional to r, it's inversely proportional to r squared. Now what does that mean? Okay, that means that if I make these twice as far apart, the force of gravity goes down by 1 over 2 squared, or it'll be 1/4 as great. If I make them 3 times farther apart, the force of gravity is 1/9 as strong as it was before. If I make them 4 times as far apart, well, you get the idea. It's going to be 1/16 as powerful. So the force of gravity drops off by the square of the distance. Now, by the way, this is a property of three-dimensional space. Anything that spreads out evenly in 3 dimensions, that just spreads out. It could be like the light from a candle. If you're shining a candle and the light is spreading out in 3-dimensional space, the intensity of the light decreases by the square of the distance. If a speaker is giving off a sound and that sound is spreading out evenly in 3-dimensional space, the sound gets weaker by the square of the distance. And gravity does the same thing. The effect of gravity, it gets weaker by the square of the distance. Okay, now, this is all Newton could do. He said, look, the force of gravity only depends on the masses and how far apart those masses are. Those are the only variables that you can change or control that will affect the force of gravity. But you may notice something a little disturbing. This is in newtons. Well, this is in kilograms. So that's kilograms squared, and r squared is in meters squared. Well, a newton is not a kilogram squared per meter squared. And not only that, there's enough, this tells you, m1 times m2 over r squared. This tells you how the masses affect gravity, and it tells you how distance affects gravity, but it doesn't tell you how strong gravity really is. How strong is gravity? Well, we have a number for that. We have what's called a physical constant, a property of our universe that makes the units work out, and it makes Newton's law of gravity complete. And we call it big G. Okay, big G. This is the universal gravitational constant. This is the universal gravitational constant. Newton did not know what it was. He could not measure it. But he knew it had to be some number. And so he came up with some estimates, and he did some experiments, and he made some observations and calculations. But he did everything with ratios, so that a big G would, quite often cancel out of the calculations. It was kind of limiting for him. But later, a guy named a British experimental physicist named Cavendish was able to figure out what this big G is. So I'm just going to tell you what big G is, and then we'll talk about it. Big G, the universal gravitational constant. It's a constant, first of all. It is a constant. That is, it doesn't change with time or distance or location or anything. It's the same everywhere in the universe, so far as we know. And it has a value, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. This is the number that you insert in here. Now this is quite long to write down. That's why we use a capital G to abbreviate it. Now it is a constant of nature. Now you've dealt with constants of nature before. when you are in chemistry, you dealt with the mass of an electron. That's a constant of nature. The charge on a proton or electron is a constant of nature. But in physics, I think this is really the first constant of nature that we've dealt with. We're going to deal with several more, especially in electromagnetism. But this number represents a property of our universe. It tells you how strong is gravity as one of the forces of nature. And it turns out that it's not very strong. Now, right now, I want you to look at the person you're sitting closest to. Now, this may disturb you, and I don't want you to feel uncomfortable. But right now, you don't feel it, but you are attracted to the person you're sitting next to. Yes, there is an attraction. Now, I'm talking about the gravitational attraction between you two. Yes, there is. Everyone in this class is gravitationally attracted to everyone else in this class, like it or not. Okay, don't be gravity phobic on me now. Okay, so it's just that the force of gravity is so weak that you don't feel it. You don't feel it. If you put your mass and the person sitting next to you, their mass, and the distance between you, and you multiply it by big G, you're going to get a very, 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 very tiny force of attraction. It'll be in the billionths of a Newton. I mean, you don't feel it. But there is an object that's very close to us that has such a huge mass that its gravitational effect is noticeable, very noticeable. Look below your feet. It's planet Earth. Planet Earth has a huge mass. Its mass is so big that when you put your mass here in kilograms and the mass of the Earth here, and R would be the distance between the center of you, which is about 2 inches below your belly button in your guts, okay, all the way to the center of the core of the Earth. That's R squared. And that's a pretty big number too. But when you multiply all this out, you get a number like 700 newtons. That's your weight in newtons. And it works out. Okay, so the law of, this is Newton's law of gravity here. Now, the force of gravity is a vector. So we want to identify it as a vector. Now, vectors have direction. This gives you the magnitude, but we need some way of saying what direction gravity is in. Well, gravity is an attractive force. It pulls things together. We have a unit vector that says, let's pull together. Okay, let's be attractive. And that's negative r hat. So if you really want to be nerdy, you can say to that certain someone that you're attracted to in other ways, you say, hey, I really negative r hat you. That means you want to be together. All right, but don't say that. Okay, you'll be single forever. So anyway, this is the universal gravity. It's Newton's law of gravity with Newton's law of gravity in it. It's an attractive force, and you can use it to solve all kinds of really cool problems. And I think I'm going to the book goes into a little more detail than you really need to right now. When we get to a later section, I'll go over some of that stuff. But if you want to read the book, I encourage you to do so. Hey, how did they figure out what big G is, though? How'd they get that? Well, here's the problem. And here's why Newton couldn't figure out what big G was himself. Here's what you need to do. You need to get two objects of known mass, and then you need to put them a measurable distance apart, and then you need to measure the force of gravity between them. In other words, you take this equation and you solve it for G. So let's do that. big G, the universal gravitational constant, will be equal to the measured force of gravity between two objects times the distance between them squared, divided by each of their masses. Okay. Now, here's the problem. If you have two objects where you know what their masses are, and you know how far apart they are, you don't that was my cell phone, sorry. You don't turning it off. Sorry about that. It's the middle of the night here, so hey, what can I say? If you know this, and you know this, and you know this, it's very, very difficult to measure the force of gravity between them. It's so tiny that it's hard to measure. Well, a good old a guy named Cavendish, Henry Cavendish, in 1798, according to the textbook, did a marvelous experiment, and he figured out what big G was. Now, here's kind of what he did. He took, here's the ceiling, he took a wire and he hung from a cable, he hung two great big old spheres like this from a relatively, you neglect the mass of this, you neglect the mass of this, and these are pretty big, pretty massive. And then what he did is he put a mirror on here. And then he took a slit of light. He couldn't use a laser. There weren't lasers yet. There weren't lasers till like the 1960s or something. So he shined a slit of light, and he bounced that slit of light off this mirror, and it made a spot on a wall. And he measured where that spot was. Then what he, and this was M, and this was M. Then he took a great big massive sphere right here, and a great big massive sphere, and put it over here. And what happened was there was a little tiny gravitational force between these masses. Now you really, it's very difficult to measure that directly. In fact, he didn't. But it was enough to attract them together with a very tiny force. And what it did was it made this twist, oh so slightly. It made it twist. Well, when it made it twist, it made the mirror change its angle oh so slightly. And what that did was it changed where this spot, this beam of light hit the wall or hit a screen or something. And he measured this distance and therefore was able to figure out what this angle was. And based on what this angle was, he could figure out how much torque was applied to the wire. And he knew, and if you knew the torque, he could figure out what this force was. And by going through all these very, very delicate calculations, he was able to figure out what the force, was able to measure the force of gravity. So he measured the force of gravity, he measured R, measured M, and was able to arrive at this value right here for the universal gravitational constant. And there are all kinds of problems you can solve with it. And and we're going to do that. So I'd like you to, that's enough, I think, to get you started on this assignment, on assignment 1 for this new unit. So let me zoom all the way out here. And so what I'd like you to do is, going back to this, you have the rest of the period. So it's almost an hour and a half to I want you to finish whatever you need to finish on Unit 5, work on the take-home test together, and work on this. You got lots to do. Please don't waste your class time. And be diligent about this, and because we got a lot to cover. All right. Well, I hope you're having a good day. I'm having a great day. Today I picked up my Nissan Leaf, and I got it, and then I drove back to school. It's about 9:30 p.m. right now, so I need to go home. So anyway, hope you all have a great day, and I'll see you on Thursday. Bye.